Hopefully this is a little better now with my volume.
Sounds good to me.
Perfect. So let me do this. Let me just share my screen here. Sorry about that. All this delay here, but yeah. Welcome to another episode of Tech Talk with Pratik. I'm Pratik Patel, your host for today. In our previous sessions, we've heard from numerous industry experts about the many different solutions that are driving the rapid acceleration of AI, from Lenovo's ready-to-deploy Gen AI solutions to Ingram Micro's Xvantage platform. For that reason, today, we'll be diving deep into a critical aspect of building AI systems, networking. As AI models, particularly large language models and generative AI, continue to evolve, the design and performance of networking have become even more essential in determining AI workload efficiencies. To help us uncomplicate this world of accelerated networking, I'm thrilled to have an expert from Nvidia with us today to discuss their groundbreaking solution. But with that said, please note, this event is designed to give you direct access to industry experts, so feel free to put your questions and comments into the chat box and we'll address them as they come in. But enough from me. Let's get to the main event. Please join me in welcoming Taylor Allison to the virtual stage.
Excellent. Thanks so much, Pratik. Yeah, let me get my slides shared here.
Okay. But before we do that, if you could just kick things off and just give us a quick introduction of your role at Nvidia.
Yeah, I'd be happy to. So, my name is Taylor Allison. I am a product marketing manager at Nvidia, and I'm responsible for our product marketing for our AI networking solutions. And so that includes both Spectrum-X, which is our Ethernet platform for AI, and we also have our Quantum 2 InfiniBand platform, which is based on the InfiniBand technology. And so in this session today, I want to take you all through what we're doing with Spectrum-X, where Lenovo and Ingram Micro are playing in this space alongside us. And I'll emphasize that everything that I talk about today is on the truck, so to speak. This isn't roadmap content. This is content that Lenovo has tested alongside Nvidia and is offered in their generative AI portfolio, and fits within Ingram Micro's solutions as well. So this is all stuff that you can use to hit the ground running, and evangelize and push these technologies with your customers and partners.
Okay, so Taylor, let me just take a few minutes here and kind of set the stage. Nvidia is revolutionizing, everything. But to stay on topic for today, they're changing the AI-driven networking landscape with its Spectrum-X platform. Explicitly designed for enhancing generative AI workloads, Spectrum-X is integrated into Lenovo servers such as the SR670v2 and the SR675v3. On that note, Taylor, could you please kind of help our audiences understand the Spectrum-X networking platform and its importance?
Yeah, sure. So Spectrum-X is a new platform that we actually introduced last year around this time at the Computex 2023 event in Taiwan. It's a high-performance networking platform that's built on Ethernet and is capable of delivering the performance needed for AI on Ethernet. And this is really an industry first. So we'll talk a little bit about why it's a challenge to do AI with Ethernet, where I'll call it traditional Ethernet has kind of fallen short. But with the latest Spectrum 4, the ASIC for Ethernet, and the SN5600 built on that, alongside the Bluefield 3 SuperNIC, Nvidia has built this new platform that delivers the high effective bandwidth and the performance isolation that you need to build what we call AI clouds, which are cloud infrastructure environments that are connected with Ethernet for the GPU fabric. All right. And Pratik, do you want me to? I can launch into some slides on this if that would be useful or.
Yeah, I think that'd be perfect right now.
Excellent, excellent. Okay, let me share my screen. Okay, so let me just get this moving. So I mentioned earlier about this idea of these AI clouds, and I kind of I want to position here some of what we are seeing in the AI space and sort of the the use cases that define it. So, traditionally we have these concepts of clouds. Obviously, I don't need to explain all that to you folks, but you need a multi-tenant environment that's capable of scalability and extensibility. And historically, it's run a lot of small scale workloads. Obviously, clouds have this ability to scale up, but often much of what might run in an EC2 instance or something like that is something that really can fit on a single server. But that's changed with AI, and we know with accelerated computing, GPU computing, with Nvidia, things are very different, and scale out is key. But there's really two scenarios that you can have these AI deployments. I'll start with the second one, which is this AI factory. And what I mean by an AI factory, I mean GPU infrastructure that is built for purpose to train a foundational model, a large language model. So think something like GPT-4. When OpenAI trained that, essentially they built a data center that was explicitly for the purpose of training GPT-4. And so it was a massive environment, tons of GPUs, all running a single workload, and essentially few users and just large models and being trained over weeks, months. And so in these environments, we at NVIDIA, we really position the highest performance networking that we offer, which is InfiniBand for the scale out, and of course NVLink within the node for that GPU to GPU communication. And this is really that highest performance fabric that this is how you get at NVIDIA. We call it speed of light, with sort of the theoretical peak performance. But that's only one type of scenario that we see with AI deployments today. There's also these AI clouds. And again, these are environments that are doing AI. They need that high performance networking to get the most utilization out of their GPUs. But they're not necessarily all training a GPT-4 model, for instance. They could be training. Well, it's an AI cloud. It's accessible to multiple different users from different organizations that are all doing different workloads. Some AI, maybe some not AI, on that same infrastructure. And so you have sort of this environment that needs the high performance that you would typically historically get from something like InfiniBand, but also needs all of those characteristics that you need for a modern cloud computing data center. So you have that requirement of multi-tenancy. You need things like monitoring and automation and essentially all these great benefits that everybody that builds clouds they see as table stakes. And so this is a new environment, and this is really where we position Spectrum X. You still get that high performance, maybe not quite as high as InfiniBand, but very, very close. But you also have all those features that are available in Ethernet, and that compatibility to Ethernet that is really pretty necessary for these environments. So I'll talk a little bit more about why these AI clouds are different from regular clouds. I kind of mentioned it earlier. Clouds back in the day, things didn't necessarily require as much scale. More scale is needed today, but it goes beyond that, and it really goes into AI being a different sort of workload than your traditional data center enterprise workloads. AI is incredibly sensitive to this coupling. Essentially, when you train an AI model, you have tons and tons of operations that are being performed on your GPUs. And then they need to propagate to all the other GPUs, and every bit of that model training is sort of instrumental in each GPU is instrumental in that training process. And that's different from sort of the legacy environment where things could be loosely coupled. Everything impacts everything else in AI. And so you're very sensitive to interference or disturbance on the network. You need this idea of performance isolation. One workload cannot be allowed to harm another workload running on the same infrastructure. You also you can't get by with standard TCP anymore. Standard, your typical Ethernet stack. You absolutely need RDMA. You need those offloads to get that high bandwidth utilization. And you're also sensitive to this idea of jitter. And what jitter is really sort of variance of latency. With AI, you're not just relying on kind of average performance. You're sort of relying on worst case performance. So, you can think of it like you've got a class of students and they're all taking a test. And once everybody's done with the test, they can go to recess. Well, it doesn't matter if you finish the test first. You got to wait for that last person to finish the test and turn it in before you're ready for recess. And AI works the same way. Essentially, you have these collective operations that can't move to the next step until every single operation is completed. And so that's this idea that you have this incredible sensitivity to latency in the worst case. You also have these elephant flows, we call them. Essentially, rather than your typical environments where you data center connectivity, you have this lots and lots of small flows, that are not huge message sizes. With AI, you have these elephant flows that are very large message sizes, and essentially, if they collide on the network, this can basically overwhelm the buffer of your switch, and you could run into something like dropped packets, which again is killer for AI. You essentially, dropped packet requires retransmission, and that retransmission introduces that latency that I mentioned earlier, that really would lead to longer training times and essentially slower time to having a finished model.
So Taylor, I did have
Yeah.
one question here.
Yeah.
We talked about latency and performance, but I think security is one of those aspects, and that's actually the question that came in. How is
Absolutely.
security addressed in this AI cloud, and who is responsible if there is a breach?
Yeah, no, that's a phenomenal question. And honestly, we could do a session entirely probably on that question and the importance of zero trust computing. But yeah, security is vital. That's an essential part of that performance isolation that I mentioned. It's not just the actual the training time of the workload. It's also this idea that these environments are kept completely separate and leveraging things like confidential computing. And Nvidia actually deploys that across the stack from the GPU to the super NIC to the switch. You need those zero trust environments, and of course in software as well. And that's one of the reasons why I'm getting a little ahead of myself, but really the two components of Spectrum-X are the Spectrum 4 Ethernet switch and the Bluefield 3 Super NIC. And that's based on our Bluefield 3 technology, which is it's a new class of accelerators. The Bluefield 3 DPUs are sort of the brother of the Super NIC, and bringing things like encryption in flight and at rest. That's a big part of what is needed for this Spectrum-X stack. So I don't really go in this session. I don't think I have any slides to really go into detail on some of the implementation there, but that's why the Bluefield is key to this solution, because it brings enhanced security and encryption functionality over ConnectX, which is of course a great NIC. But really, Bluefield offers some differentiated functionality there, especially when combined with our DOCA, which is essentially our SDK for delivering programmability to the Bluefield. All right. Yeah, happy to help there. And yeah, by the way, jump in. Pratik, I'm happy to let's have a dialogue as much as we can.
Perfect.
Um,
So if you don't
so
mind, actually,
yeah,
so
yeah, go for
you
it.
know, there's a follow-up to that question, really. It's
Yeah,
you know, if zero trust exists and with evolution of AI, if there is a breach, how is it addressed? You know, so
you know,
I'll reach out to him afterwards, but definitely if you can kind of quickly, kind of start.
yeah, yeah. I will be honest, security is not necessarily my bailiwick, but I think that the way that Nvidia addresses this is that we offer flexibility for our customers and partners. Everybody's security implementation is going to look a little different. So I guess I'll say it this way. We're positioning Spectrum X for these AI clouds and folks that know how to build clouds, and they need the network to essentially deliver that performance for AI. I think from cloud to enterprise, there's going to be different sort of organizational, institutional ways of implementing security, and having policies around this, to handle breaches and things such as that. And I'd say our goal is to kind of meet our customers and partners where they are. So if you require, like I said, that end-to-end in-flight encryption, we support things like AES and other standards with Bluefield in the SuperNIC. We have, with the Spectrum switch, there's actually an FPGA on the board of that switch that gives us this hardware root of trust that essentially is verifying that your nothing has gone awry. There's no, it's basically checking on the authenticity of the firmware that's running on the switch. That might be where you leverage those security features. Nvidia has a whole host of things. There's this Morpheus libraries, again, sort of looking at anomaly detection, on both the SuperNIC and the GPU. It kind of depends on sort of how you want to implement this, and I think, again, our customers know what they want, and it's our job to have a solution that has the functionality and the flexibility to deliver the kind of the security implementation that they need. Because certainly it'll vary. Certain and when it comes to things like sovereign AI. You have different sensitivities, different approaches, from solution to solution. So most of what I'm going to talk about here is the performance side and the features that enable the performance of Spectrum X. But it's definitely, if you have questions about the specificity of, the product level security features we have, as well as the solution level security features we have, let's take that offline, and I can find the expert to answer your questions better than me.
Yeah, thank you, Taylor. Yeah, I think that's perfect. That's great. We can definitely take this offline. So this will work great. Thank you.
Yeah, happy to help. Yeah, so I just want to introduce this, the stack and kind of some of the benefits of Spectrum X. As I mentioned, it's really an end-to-end networking platform, from the host with the SuperNIC to the cables and transceivers. I don't call them out here, but of course those are super important as well, to the switch, the Spectrum SN5600. And really what you're getting here is this end-to-end optimization, that's giving you the highest performance for your workloads. So there's a number of features. I've called them out by name a little bit. I'll go into detail a little bit more in the session, but things like congestion control, adaptive routing. This is giving you that performance isolation, and it's giving you an increase in effective bandwidth. So what we've measured, and typically what you might see with traditional Ethernet, things like your Broadcom Tomahawk, is that when you have just the off-the-shelf switches, based on off-the-shelf ASICs, you're going to get something like 60% effective bandwidth, when you're running these AI models. What we've seen with Spectrum X is a 95 or 95+% effective bandwidth. Essentially what I'm saying here is if if you've got a 400 gig connection, you're getting something like 390 gig in actual measured performance when running these AI workloads. And so essentially as close to wire speed as is possible. And with these AI workloads, they really can benefit from that. The GPUs are consuming that traffic as fast as they can. And what that higher effective bandwidth leads to, which is ultimately more important than just the bandwidth, is faster training times. And so we'll kind of double down on that in some of the subsequent slides. We talk a bit more about benchmarks, but yeah, essentially what we're doing here is we're optimizing the solution end to end for AI. And on this slide, you see this nickel optimized Rocky. I'll talk a little bit more about what nickel is and how we optimize our Rocky or our RDMA over converged Ethernet for that particular communication pattern. So, I'll summarize it before diving into the details. What we're offering here is highest performance standard Ethernet. So everything is based on the Ethernet protocol. Anything that can speak to Ethernet can speak to Spectrum-X networking. And so you get that standardization that you know and love from Ethernet, but you also have this highest performance that you need for AI. Another key to Nvidia's offerings is that we make it as turnkey as possible. And I'm sure you folks know, the customers, they know they need AI and they're ready to take the next steps for AI, but AI is a challenge. You can't just go buy a GPU box and again connect it with Broadcom and go train the model yourselves and it's not that easy. And so folks are reliant on partners like Nvidia and Lenovo who have tested all these solutions together and essentially tuned the parameters such that when you deploy this according to our reference architectures, you're going to get something that performs just as well as Nvidia's system that we have that we essentially built this solution on. So that's a really important benefit to Spectrum-X. And ultimately, what all of that means is because the network is so important, but is only one piece of the AI infrastructure bill of materials, you actually you're actually better off with Spectrum-X paying for Spectrum-X than if somebody gave you a traditional Ethernet network for free. And I know that's a bold statement, but I'll show you. We have receipts for that. That statement that essentially because the network is so important and it amplifies the value of your GPU infrastructure, it really enhances the overall return on investment of your data center. So again, the solution, it consists of the Spectrum 4 Ethernet switch and the Bluefield SuperNIC. And I want to highlight that, yeah, we support both the HGX, the Hopper-based GPU systems, as well as DX systems. Any place where you're doing AI. Okay, so let's talk a little bit about that adaptive routing technology. And I'm going to try not to go too in the weeds on some of these slides because some of this gets a little into the nitty gritty. But it's important to sort of understand. The major takeaway that I want you to have is that Spectrum-X comes as a combination of the SuperNIC or the NIC in the host and the switch. Broadcom has a bunch of great technologies, their Tomahawk line, their Jericho 3 AI, where they're doing some cool stuff with the fabric. But ultimately, when you look at the other solutions out there based on Ethernet, it's all either switch based or NIC based or DPU based. And really, to get the performance you need for AI, you need both pieces to act in coordination. And that's why NVIDIA has this, I think, unique solution here. So adaptive routing, what this is the name is a useful name. Essentially, it's a new way of doing routing on the network to load balance most effectively and get that higher effective bandwidth. Typically, when you have an Ethernet, you're doing Ethernet and you're sending data across the network. You have this sort of static routing algorithm. It's called ECMP, equal cost multipath, that is essentially not really looking at the what's going on the network when it's sending flows. It just says, okay, this switch, this port is always going to go to this other port here. And I don't care what's happening at that other port. That's my algorithm. That's where I'm sending it. And with tradition or with sort of legacy workloads, that you can get by with that. That's fine. But with these elephant flows that I mentioned earlier, with AI, you can essentially that can overwhelm a given port, and you can start to see congestion issues. So what we have is this adaptive routing technology, which is actually going packet by packet, not just flow by flow, and looking at the essentially looking at the egress ports of switches and basically routing the packets to the switch ports that the network knows are not congested. So what that gives you is really good utilization of your bandwidth in at the switch layer. The problem with that is that the packets can get, when you start breaking flows up into packet by packet, the packets can get out of order. And so essentially, you need a mechanism that will reorder the packets at the destination. And we actually, with Blue, have that. The blue field is able to reorder the data and essentially write it to the memory of the destination, either GPU or CPU memory, and write it in order. And so essentially these applications are able to benefit from this out of order or this adaptive routing without knowing that it's completely transparent to the end application. The network's taking care of it all. It arrives in order. And the application is able to benefit from that higher effective bandwidth. And this graph here on the lower right-hand side it can kind of show you a little bit of where that benefit comes into play. Essentially, what this is showing you is for a given switch at a given time, port by port, what the bandwidth that the port is actually seeing is. And with Spectrum X, not only do you have that, you're getting that 400 gig bandwidth all the time, basically, it's very consistent, and you get that consistency, which is really key for AI. That is one of the main takeaways that I want to make sure that you folks get, is that AI it lives or dies based on consistency and predictability. And that's a key benefit from Spectrum X and this adaptive routing technology. We also have this congestion control, programmable congestion control, that is essentially relieving or preventing hotspots from occurring in the network. I won't go into the details here. I'll just kind of briefly explain, but essentially, when you have congestion on the network, what you can end up with is unfairness issues, where bandwidth is not allocated the way that you would sort of expect it to be across workloads. And as I mentioned earlier, this performance isolation is key to AI. If you have two tenants running on the same infrastructure, using the same hardware, it's vital that workload A is not negatively impacting workload B. And so what we have with Spectrum X is, again, a switch and DPU or SuperNIC implementation that works in concert to relieve this congestion. You have telemetry probes on the switch that are essentially feeding data to Bluefield in hardware, saying that we see congestion starting to crop up, and you need to rate limit your sending. And so that's basically what we're doing with our congestion control. The switch detects the congestion, and the super NIC is slowing down the flow to basically prevent the hotspots from occurring and propagating down the network. And so that gives us that performance isolation. That again it ensures that all applications running on the AI cloud are able to receive the performance that they would expect to receive. So I mentioned earlier this environment that we built Spectrum-X on, and how we use that for our reference architecture. I wanna showcase it for a second here. This is Israel 1. It's a supercomputer that we built in Israel, and it's a generative AI cloud, and it's a massive system, 256 HGXs. I'll be honest, that's a huge system. It's when you see what some folks are deploying in the field, though, things get even bigger than this. But really, it's a huge system. It's got a peak performance of 8 exaflops when looking at the lower precision. And it's about almost 100 switches and thousands of super NICs. And this is the system that essentially we used to create this Spectrum-X. We've got a reference architecture. I'll give you a little more details about that in some subsequent slides, and it's all based on this Israel 1 cluster. So really, this is how Nvidia, we kind of eat our own dog food with this, building this, and then sharing what we've learned with our partners like Lenovo and Ingram Micro, as well as with our customers. And this really is the blueprint for everything we do in terms of AI based on Ethernet. I'll also just put in a brief plug for a tool that we have that you can try today. Before we built Israel 1, we actually simulated it. And what I mean by that is we have this offering called Nvidia Air, which is a platform that lives on the public cloud. It's air.nvidia.com. It's free. And essentially, you can use it to build digital twins of your network. So you can see the images on the right-hand side. We've got switches. The top image is actually it's a leaf spine, super spine architecture. And then in the bottom, you can see all the hosts with the super NICs inside of them. Those are all HGX servers. And essentially, this lets you simulate the entirety of your network. You've got your adapters, your cables, and your switches. And each of those switches in the simulation has a virtual machine of the network operating system that we use for Spectrum-X, the Cumulus Linux. And so you can basically test anything, your automation, your security policies, patches that you might install in this digital twin, and see how those virtual images of Cumulus will react before you push anything to production. So we leverage this to essentially accelerate the deployment of Israel 1. All of the automation, all of the monitoring. You can see how the digital environment responds before you push any of it to production, and that essentially accelerates your time to your time to usability, your time to train from the virtual environment. So if you're curious, check it out. We'd be happy to let you know more about this Air tool. It's really powerful, and we've got a lot of customers and partners that are leveraging it today.
I put a link in the chat, Taylor, so definitely the audience
Perfect.
can click on it. Yep.
Yeah, take a look. It's really cool. So I mentioned this reference architecture, and it with thing to tell you, offering to be all about how great the performance is, and tout all these. Another thing to actually implement it and to know how. Earlier this year, I think in February, we released the version 1.0 of our SpectrumX reference architecture, and this is I think where the magic happens. It's a reference architecture that defines this scalable unit-based implementation that is seamlessly scales from one SU to hundreds of SUs and even more, and essentially shows you how to build this as a leaf spine or leaf spine super spine network. And I mentioned earlier that the Israel 1 design is actually a leaf spine super spine. It's actually, it didn't have to be 3 tiers. We made it 3 tiers because that allows us to build this reference architecture to scale beyond the size of Israel 1. So essentially what this is offering is a cookbook of the bill of materials, the deployment guide, the commands to essentially set up your network, and basically the proper thresholds to get the performance that I mentioned. We suggest this is bundled alongside our professional services and our enterprise support offering. And again, essentially, it's our implementation to make this AI on Ethernet as turnkey as possible. So with that reference architecture, if you have 2 tiers, you can do up to 8,000 GPUs in your cluster. Here's an example of that topology. Something that I won't dive too much on. The reference architecture is based on topology, and what that means is essentially you have GPU connectivity that is it's not all the GPUs connected to a top of racks where every it is within one hop of each other are all in the same rack. It's actually a logical organization where essentially you have your scalable unit, and in that scalable unit, GPU 1 from server 1 talks to GPU 1 of server 2, server 3, all the way up to server 32. The distinction there is that lets us do some clever things with this NCCL library. And I mentioned that earlier in the session. NCCL stands for Nvidia Collective Communications Library. And it's a set of, essentially a set of tools that all of your AI training consists of. So I'll talk a bit more about this, but there's these 2 operations, all reduce and all to all, that are essentially where your GPUs are communicating with each other. All reduce is within a single scale unit, or not having to go beyond 2 tiers. All to all is all of the GPUs in your, running the same training job, talking to each other. And basically every AI workload, every training workload consists of just tons and tons of those all reduce and all to all operations. So we designed the network to really cater to that. All right, and so I mentioned 2 tiers. There's also this 3-tier design with a leaf spine and super spine. Something that I didn't. I'll actually jump back a couple slides. A quirk to this. I mentioned that it's not necessarily all the switches or all the GPUs in a given rack. They talk beyond the rack, and what that necessitates is actually different rack design. Let me put my pointer on. You can see here, in this diagram, you've got these larger boxes are your HGX GPU servers, and then you have all your switches actually in one rack, and they call it a middle of row or an end of row switch design. And so, again, in this scalable unit, this server, this server, this server, all of these servers might be talking to the same, or will be talking to the same switch. It's just one GPU in that server is connecting to that one switch. So that's kind of how that rail optimized design shows up in your your actual data center build out. Okay, so jumping back, we talked 3 tiers here, and this is absolutely massive scale. With 3 tiers, you can actually go up to 512,000 GPUs. And I remember when I built this slide, it was maybe a year ago, and I remember thinking how absurd this slide was. When will anybody ever be at that scale? It's funny because earlier today, the timing's perfect. Elon Musk just announced the news of his 100,000 GPU cluster based on H100, and so I know this scale is absurd, but it's also absurd how quickly we sort of got to this scale and the necessity for designing networks at this scale. So that's something that we can do with Spectrum-X going out to 3 tiers. You can scale to absolutely massive numbers of GPUs. So that's basically the reference architecture. What I want to talk to you guys now about is some of the results. I mentioned a bit earlier about how we get this 1.6 higher effective bandwidth for the network, which is a nice number. It is important to have high network utilization. But at the end of the day, we do all this so that you get better outcomes with your AI models. We want something that's application specific, kind of at the top of the pyramid. So what I'm going to take you through is how we've seen great results at each layer of the stack. And the goal of this slide is to show you how these things build on each other. And so how when NVIDIA builds the solution, we have to optimize at every level. Was there a question? Okay. So I'll show you a set of benchmarks that essentially go through this pyramid that we have here. Ultimately, all of this comes from the fact that we're building our own switches and SuperNICs in-house, and we design the hardware for best of breed performance. But we see that performance when we run RDMA, and we verify that we have a healthy RDMA fabric, and it can support Rocky effectively. Rocky, in turn, is key to those nickel workloads that I mentioned earlier. So the all reduced and all to all are highly reliant on efficient offloading from Rocky, and those are the AI collectives that support the specific models themselves. So we'll talk about GPT, Facebook's FSDP Llama, Nvidia's Nemo, which is essentially our in-house version of GPT. When we tune the Spectrum-X and we release these reference architectures, we're testing all of these LLMs and tuning the network to give highest performance for them. So I'll start with RDMA and essentially showing that we have this healthy RDMA fabric. I've got 3 categories here. We've got the traditional Ethernet, and what that is essentially, the idea is that it's running Rocky. We're assuming something that an Arista or another vendor might do. Obviously, they would use Rocky. They would use things like ECMP, and they would have a congestion control from things like ECN and PFC, sort of the typical Ethernet stack for AI. And then we have Spectrum-X, which is our in-house innovations that are layered on top of that. And then we have what we call the theoretical peak, which is essentially, you in-house we call it speed of light, but it's basically, what you would assume to be wire speed if you just had the completely perfect scenario, which we all know in practice, you never, it's like speed of light, you can never quite reach it. But with Spectrum-X, what we see is that for RDMA, looking at bandwidth, we actually do get very, very close to that theoretical peak, and it's about 4 times higher than what you see with traditional Ethernet. So that's our bandwidth story, and with latency we see something similar. With latency, obviously, lower is better. So we're measuring this in microseconds, and with Spectrum-X, we've got about 4x lower latency than traditional Ethernet as well. So again, what this kind of shows, you can't extrapolate this into AI application performance, but it does show you that the network itself is giving that highest performance and kind of doing what it should. Next, we looked at those nickel operations, and I mentioned two of them. There's all reduce and all to all, and this is all reduce. And I just want to, the title may seem a little confusing here, but we have this isolation idea, and what that means is this is supposed to simulate an AI cloud environment. And what I mean by that is you have one application that's running nickel. And then on that same infrastructure, you have other applications that are doing other things. They're doing all sorts of different things. Maybe running AI, maybe not, maybe something completely different. And so we simulated that by having some nodes essentially doing the workload and some nodes that were just creating noise. And what we saw here was that actually with Spectrum-X, you're essentially getting as you're almost hitting that theoretical peak. And what that means is you're essentially seeing performance that is the same as if you didn't have those other nodes chattering along and creating noise. So really, we're getting that really high performance with Spectrum-X. With traditional Ethernet, of course, it falls off significantly, but it also shows some variance. And so you can see here, we capture both the average number and the max number. And it's tempting to sort of say, well, the max is sort of more useful. But again, AI is so dependent on consistency and predictability. And so, if you buy infrastructure to train a model, and you don't know whether it's going to take 3 months or 4 months, that's a really big problem for your investment. So here we see that traditional Ethernet is not up to the task of delivering that performance that's needed for AI. Next, we'll talk a little bit about the actual applications themselves. And what I have here, I've only got one of them in this deck, but I can tell you, and we can certainly provide it, that whether you're talking FSDP Llama, which is Facebook's large language model, or ChatGPT or GPT, or Nemo, the Nvidia version, we're seeing significant gains, anywhere from, I'll say, 1.2 to 1.5x higher performance on at the model scale. And so what I mean by that is, what we're looking at here, this graph is measuring training time, and so the training of the model consists of a number of steps, and this is actually the training time per step. And what you're seeing here is in seconds. The environment with Spectrum-X is training in 15 seconds, and it's taking 26 seconds for the environment with traditional Ethernet. And so what this means is, with Spectrum-X, your models train faster. You have them ready to operationalize faster, and you have them ready to benefit from. You get the benefit of AI faster. Another thing that I want to call out, again, kind of doubling down on that consistency and predictability story. With AI clouds, you have multiple jobs running on the cluster, and the way that would work in principle is, different servers or even different GPUs could be reserved for different jobs. And with an AI cloud, because you're trying to utilize as much of that infrastructure as possible, you don't necessarily have your jobs carved up in a way where you have this best case for job placement. So maybe you have a case where all of your nodes are able to talk through the just talk directly through leafs, and that's kind of what you see here with this best case scenario. But what's more likely is that you have some nodes that are able to communicate via leaf, and some nodes that, to get to the rest of the nodes, they got to go through the spine. And so, here you've got job 1 and job 2 are both sharing the same leaf switch. And so you have a case where, a bit of inefficiency. And then, of course, there's the worst case where, all of your jobs are having to communicate across the spine layer to share the traffic that's going from GPU to GPU. And that can actually result in substantial differences in performance. You can see here the effective bandwidth from the optimal case to the average and the worst case falls off significantly. And in each case, you have this high jitter where your performance is varying significantly from run to run. So that's what happens with traditional Ethernet, and this can be a really big deal for AI. With Spectrum-X, we actually see that not only does it not matter how the jobs are allocated on the compute infrastructure, your performance is high across the board, but it's also consistent across the board. And so even in that worst case scenario where all of your jobs are having to go, they're having to jump through more hops than you'd expect, we're still seeing high effective bandwidth. We're still getting good utilization of our infrastructure. We also, another key need for AI is resiliency. These AI clouds they consist of massive numbers of GPUs, switches, cables, and it's just statistical that the infrastructure is going to fail. I think we all know that in these large data centers, there's just so much equipment that something is going to have an outage occasionally. And AI again is really sensitive to that, because if you have an outage and you have this sort of static implementation across a particular link or set of links, and they go down, then that's a set of GPUs that can't be accessed as quickly, and so a set of GPUs that aren't getting their updated AI data, to update their parameters, and then essentially a set of GPUs that will cause the whole infrastructure to hang. So AI is very sensitive to link failures. And what we can do with that adaptive routing, as I mentioned, with this load balancing that we have via Spectrum-X that's super fine-grained, we can actually route around those link failures using basically that ECMP or a variant of ECMP, and rebalance the traffic to keep the networks essentially to keep bandwidth pretty constant bandwidth utilization across all of those switches. So you can see here that even with links down, and of course performance does degrade when links go down. That's just a given that you're losing links. It's basically a tautology. We see much higher performance for the network with Spectrum-X versus traditional Ethernet, because again, when you have that static routing, you're not able to rebalance those flows and avoid failed paths. So that's about it for the performance data that I mentioned. But I wanted to come back to that statement that I made earlier in the session, kind of a bold claim about how the network basically pays for itself, and I wanted to explain that with some data around the TCO. As you can see here, if you start pricing out your environment, and I will say, you can we could probably haggle over any of these given numbers, and that's not really the point, but essentially, the net of this is that the majority of your spend is having to go towards the GPU infrastructure. The network is just a small piece of the overall TCO of an AI data center. But when we talk about those performance benefits that I mentioned for things like Llama and GPT, you're talking data center wide benefits. You're talking a data center wide benefit of 1.4x higher performance or 1.3x higher TCO. And what that translates to, it's coming from the network, but it applies to that entire infrastructure. And so what you can see here is that even though Spectrum-X is not necessarily the lowest cost network implementation, and I will say Nvidia, we don't position ourselves to win on cost. We position ourselves to win on performance and TCO performance. And so what you can see here is that even though your TCO at, sort of getting started is higher with Spectrum-X, you're getting higher utilization, higher value out of, and higher return on investment out of the Spectrum-X cluster. So essentially, again, and you can see that value when you look at those performance benefits is 21 million, which as mentioned is higher than the cost of the entire network. So it's a really powerful thing that we have in networking. Our value goes beyond the just the cost of the switches and adapters themselves. And so that's part of the power of Spectrum-X. And I'll wrap it up here by saying, this is it's really important for these big clouds. It's also even more important, I think, for enterprises. Again, I mentioned at the start that setting up AI is hard, and getting the most utilization out of your infrastructure. It's not a given. If you buy something that isn't, you could try and do this yourself. You could replicate what we've done with Spectrum-X. Again, we are standard Ethernet, but it would take a long time, and again, without the differentiated hardware that we offer, you wouldn't quite get the same result. But that's really where the power of Spectrum-X comes, I think, is that we have this reference architecture that's based on real world experience. We have automation tools that allow you to roll it out fast. We do all the testing in-house. We're optimizing on these AI models so that you don't have to. We feel we have the in-house experts, the nickel architects, the folks who build the switch hardware to set the parameters. And we put it into this reference architecture and we make it available to you. And so you can get that performance without adding complexity. And I think you can see that Spectrum-X is offering all that just by looking at where it's sold and who's adopting it. And as you know, it's available through the tier 1 OEMs, and in particular Lenovo is really close to market with us. We're training them all the time. We're working with them on designs. They have a great reference architecture out there around their OVXL40S. And as Pratik mentioned, they also have they've got the HDX H100 support as well with their new systems. And not only do they offer Spectrum-X and the GPUs, they also offer Nvidia's hardware or software stack with things like Nvidia AI Enterprise. So really, it's this connectivity that's end to end, and it's a one-stop shop from folks like Lenovo and working with Ingram Micro. You have all the tools that you need for AI. Okay, I think that's it. That's my last slide.
Perfect. Yep. Thank you, Taylor. I really appreciate this. I actually had a training, the InfiniBand Spectrum-X training a couple months ago, and I knew I had to put it on my line card for one of these series. So definitely, I really appreciate it.
Yeah, wonderful. Thanks for having me, and happy to answer. Just reach out if there are any questions.
Perfect. Yep. So huge thanks to Taylor for sharing his expertise, and to all of you for tuning in. Make it a terrific Tuesday. Have a great week, everyone. Goodbye for now.
You too. Bye.